Hello everyone and welcome to this Zoom presentation on Titan.
Let's begin with some fundamentals. Titan is a moon of Saturn, and it is one of the most extraordinary moons in the solar system. In fact, it's a moon that is almost more like the Earth than any other body in the solar system. So let's start with a diagram of the solar system. And what I meant to say at the beginning is that I'm not going to assume any astronomy knowledge at all, because I know there are people in this presentation who haven't come across astronomy very much before. So this is a diagram of the solar system with the sun on the left. You can barely see it. Well, you can see only as part of it because it's so enormous compared to the planets. And the 8 planets of the solar system as they are arranged in order and distance from the sun. Just a moment, I'm just going to admit 2 more people. And so the solar system arranges itself rather neatly into the 4 inner planets, Mercury, Venus, Earth, and Mars. And these are the so-called terrestrial planets. They have a hard surface that you could stand upon or land a spacecraft on. And we are, of course, living on the Earth, the 3rd planet from the sun. And then we have, on the outer solar system, we have the 4 gas giants, Jupiter, Saturn, Uranus, and Neptune. And as I say, Titan is a moon of Saturn, and a moon is an object that orbits a planet rather than orbiting the sun directly. Now, the distances between the planets are not representative. They are not to scale with their sizes, and that's because the real distances between the planets is enormous, and they're extremely sparsely distributed in the solar system. And in fact, Saturn is approximately 10 times further away from the sun than the Earth is. And that means that it receives about 1% as much sunlight as the Earth does, and therefore so does Titan. And in fact, on the surface of Titan, the levels of light are 0.1%, about 1,000th of that on Earth, which is about 500 times as bright as a full moon, but about 1,000 times less than sunlight, as I say, during the day. It's about the sort of levels of light that you would get 10 minutes after sunset. And the other important thing about being so far away from the sun is that the primary building blocks of these planets and moons in the outer solar system is ice. And just a second, I've got more people to join. Is ice. And that means that ice forms a significant building block of the moons of the gas giants. Most moons in the solar system orbit the gas giants, and therefore Titan is one of those. And Saturn has the most moons. It has 82. Hi, Dan.
How did you turn the sound up?
On the side there. Yeah, top.
Very top, yeah. Yeah. There you go.
And Saturn, so I don't need to show you this picture of Saturn because Titan is a moon of Saturn, but Saturn is so beautiful that I have to show you this picture with its exquisite ring system. So, Titan. So this is a representation of how far away Titan orbits from Saturn, and it's to scale. So the distance of Titan here. So Titan is this blob on the right-hand side, and Saturn is the planet here. So you can see that it actually orbits at a distance that is much further than the rings are from Saturn. And it orbits Saturn in just under 16 days. And like our moon, it always keeps the same face towards Saturn. So if you were standing on Titan and you were standing on the side of Titan that was looking at Saturn, Saturn would hang in the sky permanently in the same position. And it would be 11 times the size of the full moon with its beautiful ring. So it would be an incredible sight. Now, not only that, but Titan orbits Saturn not in a circular orbit, but in an elliptical orbit, which means that its distance from Saturn varies quite a bit. And that is very useful to understand what Titan is actually made of inside. And I will describe that later. So when we think Titan is a completely extraordinary moon, it is completely different in many, many ways to all of the other moons in the solar system. So it is not typical at all. And when we think of moons in the solar system, we probably think of moons like this. Now, these are three of the 205 moons in our solar system, 205 known moons. And the images here are definitely not to scale. So on the left here, we see our moon. It has many prominent craters, and it has these frozen lava flows in grey here, which are called mare. We have Mimas here, which also is covered in craters, with a very large crater here. It's sometimes called the Death Star moon because of its large crater. And on the right-hand side here, we have Phobos, which also has many craters. So typically, this is how we think about moons: grey, covered in craters, possibly made of cheese, and importantly, very, very or little or no atmosphere at all. And without an atmosphere, there cannot be any interesting interactions of an atmosphere with the surface, like erosion. There can't be rain, there can't be global circulation of the atmosphere, there can't be a rich chemistry. And in addition, most importantly, there cannot be any prospect of life. But when we look at Titan, and this is an image of Titan taken by the Cassini orbiter, which I will talk about later, in the visible wavelength. So this is light that you see with your own eyes. So if you were near Titan, this is how Titan would appear. And you can see that it looks like a fuzzy blob, which to the casual observer might think that Titan is therefore quite uninteresting. But it's that fuzziness, it's the fact that it has such a substantial atmosphere, which makes it a fascinating place. Because suddenly we have all the things that I listed before that aren't present for other moons at Titan. And in fact, we have a rich chemistry, a substantial atmosphere, there is erosion, and as I will explain later, there is a lot of liquid there as well, which makes Titan so interesting. The atmosphere itself, the atmosphere itself, and this is where we see the first similarity with the Earth. The atmosphere of Titan is almost all nitrogen, or a very high fraction of it is nitrogen. And the same is true of our atmosphere. But other than that, it's 5.7% of methane. And we also have a tiny fraction of hydrogen. And there are many other interesting molecules in the atmosphere as well. Just a second, I need to mute. Can everyone mute their microphone, please? Thank you. So it's because of this atmosphere that is not present substantially in any other moon of the solar system that makes Titan so fascinating. So
else helping him because he's got to let everybody in otherwise.
Just a second, sorry. So when we look at this, is a diagram of the moons of Saturn, their relative sizes, most of them anyway. Some of the smaller ones are shown larger than their true size. But the main point is that Titan is overwhelmingly the largest moon in the Saturn system. And it's thought that Titan was probably formed or as a result of collisions of previous moons, and the result of those collisions has resulted in a Titan-sized object and many other objects which are quite large, not as large as Titan, but are the result of those collisions. And a similar story is thought to be true of the planet Jupiter as well. So here we see Titan and compared in size to the Earth and the Moon. Now it turns out that Titan, on the bottom left here, is a planetary-sized object, even though it's not a planet. It is larger than the planet Mercury, and it's substantially larger than our Moon. In fact, it's the second largest moon of our solar system. It's about 50% larger than our Moon. It's substantially smaller than our Earth, but nevertheless, amazingly, its atmosphere is larger, 25% larger than the Earth's, and the pressure at the surface is 50% higher than the Earth's. So in fact, Titan has the second most significant, second most massive atmosphere in the solar system of all the solid objects in the solar system. If you exclude the gas giant planets, it has the second largest, the largest being Venus, that of Venus. So here is a very brief timeline of Titan. And Titan was discovered in 1655 by Christian-Huygens, and we see him pictured on the left here. And I love Christian-Huygens. He has mainly because he has a fabulous hairdo. It's obviously, of course, a wig, which was fashionable at the time. But here he is posing for us in the camera, and he looks rather magnificent. He's often referred to as the Dutch Newton because he was a bit of a polymath, a bit of a genius. He invented the pendulum clock, and he also invented the mathematical theory of the wave nature of light. And he was also a dab hand with his hands, and he greatly improved on the telescope that Galileo had used 45 years earlier to discover the moons of Jupiter. And it was Huygens who was inspired by Galileo's discovery of the 4 largest moons of Jupiter, Io, Europa, Ganymede, and Callisto, that inspired him to try and find other moons in the solar system. So he got together with his brother Constantine. He improved Galileo's telescope, and in 1655 he was successful. He didn't call it Titan, he called it Saturni Mundi. It was called Titan in the 19th century by John Herschel, a famous astronomer. His father was famous, William Herschel was famous for discovering the planet Uranus in 1781. Subsequently, in the mid-20th century, the great astronomer Gerard Kuiper, who is of Kuiper Belt fame. The Kuiper Belt is the belt of very cold objects in the outer solar system that is thought to be the source of many comets and dwarf planets. He discovered methane using a spectroscope, looking at the light from Titan and putting it in an instrument that spread the light into its different wavelengths. He discovered methane in the atmosphere. And then when we had the first spacecraft visiting Titan in the 1980s and late 70s, the Pioneer and the Voyager spacecraft, they didn't stay around very long. They were flyby missions, but they took the first close-up images and measurements. And in 1980, Voyager detects nitrogen in the atmosphere and determines Titan's physical properties, its mass and size and so on, accurately. And then we have a sea change in our understanding of Titan with the Cassini-Huygens mission. And much of my presentation, much of the rest of the presentation will be devoted to that mission. And I will describe it in more detail in the next couple of slides. But anyway, Cassini arrived on July the 1st, 2004 at the Saturn system. And then amazingly, Cassini took with it a spacecraft, another spacecraft, which piggybacked on Cassini, called Huygens, named after Christian Huygens, the discoverer, of course, of Titan. And this spacecraft landed on Titan on January the 14th, 2005. And that was an extraordinary landing, and I will describe that later. One of the most amazing events in the history of space science. So here is a summary of the Cassini mission to Saturn, a breathtaking mission. So on the left, you see an image of the spacecraft before it was launched in a building that we call AIT in the space industry, Assembly, Integration and Test. And you can see that it's enormous. In fact, it's nearly 7 meters high, or it was. It doesn't exist any longer, as I will describe later. And you can see it in comparison to the engineers at the base of the photograph, just how large it is. The large dish at the top is its high gain antenna, and the object on the left, this gold image here, is the Huygens probe. And here we have on a graphic of the Huygens probe, the Cassini and Huygens probe together at Saturn. And Cassini was launched in 1997 and took 7 years to get to Saturn. And you might imagine that it traveled there directly, but that is impossible because it's so massive and it would take far too much fuel to do so. So instead, a trick was discovered a decade before this, whereby a spacecraft could use the inner planets, the closer planets to the solar system, to gain energy, to give energy to Cassini as it flew by those inner planets. And so on the way to Saturn, it actually had to go in towards the inner solar system first. And it orbited the sun, bypassing Venus twice, and then the Earth, and then an asteroid, which I think wasn't really necessary, it was just showing off. And then it bypassed Jupiter. And that gave it sufficient energy to get to Saturn in 2004, July 2004. And to ensure that it didn't zoom past Saturn, it had to fire its retro rockets and brake. And that took half of its fuel to do that. And then it entered into the orbit of Saturn and orbited Saturn for the next 13 years, making measurements of the extraordinary Saturn system, of Saturn itself, its moons, and its beautiful ring system. Here we have a photograph, another photograph on the left, nearly 7 meters high, over 2 tons, the actual orbiter itself. The spacecraft, the Huygens spacecraft, was 349 kilograms, very, very substantial. And more than both of those put together was the propellant mass, the actual fuel that got it there and allowed it to brake at Saturn and to perform all the orbital maneuvers to bypass, to fly by many of the moons of Saturn as it orbited Saturn. That was 3.1 tons of propellant, so it's extraordinary. And here is the Huygens spacecraft, again in AIT, and you can see it's a gold coloured. It has a clamshell appearance. The nearer, it's in 2 components here with 2 engineers. The spacecraft itself, the Huygens probe itself, is nestled is the sort of tub-shaped object within the outer back clamshell, and the front part of the spacecraft is the heat shield, and the heat shield separated from the main spacecraft as it descended. So Huygens was, of course, had several instruments on it, and the idea of those instruments was to measure the physical and chemical properties of Titan in as many ways as was humanly possible. And so the Huygens atmospheric structure instrument, the first one listed here, measured the physical and electrical properties of the atmosphere, such as temperature and pressure. And it also measured the density of the atmosphere, and it could detect gusts of wind. The Doppler wind experiment allowed scientists to understand how fast, with respect to Cassini, that Huygens was traveling away from Cassini. And that allows the measurement of wind speed and how much the Huygens spacecraft is being buffeted by the wind. Unfortunately and heartbreakingly for the team that created this instrument, all the data was lost because one of the channels was lost and it wasn't broadcasted on both channels. However, all of the science was recovered by ground stations on the Earth that were also measuring the same information from the spacecraft. The third instrument on this slide is the descent imager and spectral radiometer. And what it can do, what it takes is images and what are called spectra. So spectra is taking the light from the surface and from the atmosphere, spreading that light out into a graph and seeing how much light from all the different wavelengths of light that you get. And that allows scientists to determine what the atmosphere is made of. And it also could measure what are called the density of aerosols. So aerosols are droplets of liquid that are in the atmosphere of Titan, which were known to exist at the time. This is the second of the 2 slides. So this top instrument is a complicated sounding and is a complicated instrument, but the gas chromatograph and mass spectrometer. But its purpose is easy to understand. It was trying to understand what the different molecules were in the atmosphere. A very complicated thing to do, but that's what it was doing, and trying to identify how much of each type of chemical was in the atmosphere. The second one is the ACP, the aerosol collector and pyrolyzer. And what that did is that those droplets of liquid that I talked about, what scientists call aerosols, it allowed those aerosols to be collected. So amazingly, it was able to take bits of the atmosphere as it descended, as it dropped through the atmosphere of Huygens and passed them through to the GCMS above to identify what those chemicals were. So very complex and amazing instruments. And lastly, we have something called the surface science package. And that was an instrument that was the first thing to hit the surface of Titan when Huygens landed. And it had a probe on the end of it that, as it hit the surface, was retracted into the Huygens probe. And how fast it was retracted allowed scientists to determine how hard the surface was. So if the surface was very hard, it would get retracted and what was called slow down very suddenly. If it was softer or there were objects in the way, it might slow down in a different way, suddenly slowing down and then more slowly slowing down. It could also measure the speed of sound and how in the atmosphere, because Titan has air, has an atmosphere. It's not like our air, it's made of nitrogen and methane and hydrogen, and lots of other things. Because it has an atmosphere, that allows sound to travel, and it allowed the speed of sound to be measured. And if you can do that, that can give you an idea of what the atmosphere is also made of and how hot it is. So I'm now going to take you through a group of stills that allow you to understand what was happening sort of over the sort of key frames, the key stages of the landing of the Huygens probe on Titan. So prior to this point, Huygens had been let go by the Cassini orbiter on Christmas Day 2004. And it was effectively dropped. So it descended free fall. And it took 3 weeks to enter from being dropped by Cassini, or pushed actually, it was pushed by Cassini via some sort of springs effectively. And it was pushed towards Titan, and it took 3 weeks to land. And it's getting faster and faster and faster as it does so. Now this is amazing if you think about it, because Cassini and Titan are also going around Saturn as this is happening. And because it takes 3 weeks, Titan is actually orbited Saturn 1.5 times, and Cassini, all the time that it's happening. And in fact, Cassini, after it was traveling towards Titan as well, and it had to push itself out of the way to make sure that it too didn't enter Titan. Anyway, so this first image isn't a photograph, it's actually a simulation, but the next ones will be photographs. And so what's happening here is that the probe, after 3 weeks, is actually hitting the atmosphere at 25,000 kilometers per hour. And it's being slowed down by the fact that the atmosphere is quite thick. And within a few minutes, it slows down to 500 kilometers per hour, and it's at 150 kilometers altitude. And then a main parachute opens, which slows it to 300 kilometers an hour and 114 kilometers altitude. And then finally, there's a parachute which stabilizes its descent and allows it to enter a lower, denser part of the atmosphere, down to 56 kilometers altitude and 140 kilometers per hour. Now we are seeing Huygens inside. It's beginning to image the surface of Titan. And so we're now looking at a world which is 1.5 billion kilometers away, just under. And on the left, well, what's happening is that Huygens is approaching a dark valley between higher, brighter, hilly regions. On the left, you can see a pair of dark parallel lines to the left, which are part of a vast system of dunes which surround the moon. And then still on the left, but on the lower left, we see a complicated system of drainage channels. Some of these are hundreds of meters wide and kilometers long, and these are cut into the hillside. So you can see that there are features on Titan that are similar to the features that we see on Earth. And this is yet another similarity with Earth. And this is indicating that there are probably liquids on the surface of Titan, and they're thought to be the runoff of liquid methane rain. And I will talk about that a little bit more. And there are images, so stereographic images, which means 2 images taken at the same time but from slightly different positions either side of the Huygens lander. They show that the hills on the left are about 200 meters tall, while the features in the valley are about tens of meters in height. So that's the sort of range of heights that we get on Titan. In fact, there are almost no features that are greater than 700 meters high on Titan. So it's not particularly mountainous. So bear with me. This next slide, we see that Huygens is actually about to land near a water ice cropping ridge. No, I've skipped ahead a little bit. This is the water ice cropping ridge. So here we see another western view of the descent of, beg your pardon, sorry, I've got a little bit lost. A western view of the descent of Huygens from about 32 kilometers. And this affords a good view of the drainage channels and the shoreline, the apparent shoreline that we see on the right-hand side. There are more dark lowlands up here, and a rough pitted hillside is to the left. Now, measurements show that these bright areas are likely to be water ice, and the dark areas are likely to be a mixture of sort of hydrocarbons, whose composition is unknown. They're thought to be a class of compounds called thiolins. Okay. So we have now a phenomenal picture, I think at least, of the surface of Titan. And you see a picture which looks kind of familiar. Yes, it's orange, but you could imagine this could come from the Earth. So in the foreground, we see rounded pebbles. And these pebbles are about the size of a fist, to about a meter in size. It's that sort of size. And they are rounded. And that's important because it shows that almost certainly they were rounded by a liquid on the surface of Titan. Now, liquids on the surfaces of objects are extremely rare in the solar system. In order to have a liquid on the surface of an object, you need a substantial atmosphere. So that eliminates almost everywhere in the solar system, all the solid objects, as I mentioned before. And you also need it to be cool enough to make sure that that liquid remains a liquid and isn't boiled off like it would be on Venus, for example, which has a very substantial atmosphere, but is very, very hot indeed, too hot for any liquid to survive. And there are only two places in the entire solar system where liquids can exist on the surface, and that is the Earth and Titan. So this is yet another way in which Titan is similar to the Earth. The hills in the distance are a few tens of meters in height, so not very mountainous. The other thing that you can see in this diagram, and on the left, you have a picture which is the correct ratio, if you like, the correct aspect ratio of height to width. The main picture has been stretched to fill the slide. But in the main part, you can see a dark area beyond the rocks, but before the further area in the distance. And this is the shadow of the parachute that came off the lander, or had been jettisoned from the lander just before it landed. And one more thing is that when the spacecraft landed, it boiled off some methane. And you can see this on the lens of the camera. There's actually a dewdrop on the camera. And this is liquid methane that has been vaporized by the heat of the landing and appeared on the spacecraft. And the spacecraft amazingly survived for an hour on the surface. It was also designed to land on liquid just in case because that was a real possibility. We didn't know whether Titan would land on liquid or on solid, but in fact it landed on a solid surface that probably was liquid in a quite recent past. So that's beautiful. And here we have two more pictures, which are similar and show the raw images that were taken by the spacecraft. They probably remind many of you of the surface of Mars, the right one especially, because of its orange tint and the showing of the different cobblestones. But unlike Mars, these cobblestones are rounded by the action of liquid. There is not thought to be any permanent liquid on the surface of Mars. So what did Huygens tell us? In fact, of course, it told us a great deal, but I've tried to summarize it here. So one of the instruments, the Huygens atmospheric science instrument, if you remember, that was the one that measured the properties of the atmosphere as it descended. determined the surface temperature to be minus 179 degrees centigrade. So that's incredibly chilly. And it's only because it's so chilly that we can have liquid methane on the surface. That explains why we have liquid methane. You could have it if you had a very high atmospheric pressure as well, but that's not the case. Two other instruments showed that there are very, very powerful winds at 120 kilometers altitude, but only very slight winds at the surface. So this is one of the mysteries of Titan, is how do many of the surface features form without very strong winds? Also, the moon has what's called super rotation. Excuse me, and that means that the upper atmosphere, the air very high up, goes round Titan much faster than the moon orbits itself, a bit like Venus does that. And one of the other instruments, the aerosol collector and pyrolyzer, that collected liquids, if you remember, from the atmosphere, the droplets of liquids, it discovered that the atmosphere contains organic compounds. So that's what that means, is it contains molecules, which are groups of atoms joined together, and that many of those have an atom called carbon in them. Now, many of the molecules in our bodies contain carbon, and we are carbon-based life forms. So discovery of carbon in the atmosphere of Titan and in the molecules of the atmosphere of Titan is very exciting if you are interested in whether life could arise or has arisen on a particular body. And we know for certain that these carbon compounds, as they're called, exist on Titan, which is very interesting, and yet another similarity with the Earth. So there was another instrument, the descent spectrometer and infrared radiometer, so that could measure what these liquids in the atmosphere were made of. And it showed that they are consistent, at least, with this substance called thiolin, which has been made in, which chemists have made in labs on the Earth by taking a mixture of gases that are present in Titan's atmosphere and putting an electric charge through them to see what would be made. And they make these molecules called thiolins, and these thiolins have also been discovered in the atmosphere of Titan. So, so amazingly, another similarity of Titan to the Earth is that Titan has not what we have on Earth, a water cycle, but it has something very similar called a methane cycle. What that means is that although on Earth we have rivers and seas that evaporate into the atmosphere, they form clouds, and then we have rain, which then flows back into the rivers and seas, either directly or via the land. We have exactly the same processes on Titan. And that's yet another similarity, and a very important one, and it's what makes Titan so fascinating to astronomers. There's a haze in the atmosphere, and we know now that the composition of the ground is a bit like that of damp sand. It consists of a mixture of liquids, hydrocarbon mixtures, which I think of a bit like tar and ice chips. And as I mentioned before, there was a surge in liquid methane on landing. So one thing I don't think I mentioned is that because Titan is mainly, a substantial fraction of Titan is made of water, that the mountains and the rocks of Titan are actually made of water ice and not rock so much. There is some rock, but mainly water ice. But at these low temperatures, minus 179, they behave like rock. So here's a sort of cross-section through the atmosphere. So what we're looking at here is what the atmosphere is like on Earth compared to Titan. And Titan's atmosphere, which are the gases that surround atmosphere, is much, much higher than those around the Earth, 10 times higher, because it's got more of the gas. It has more air than the Earth, and it's also smaller than the Earth. So that means that the atmosphere is more extended because it doesn't have so much attraction. The air isn't so attracted by gravity as it is on Earth. But you can see there are similarities. So there is rain in both the atmospheres. They both contain nitrogen and another element that we call argon. But there are differences as well. So Titan has methane, a great deal of methane in its atmosphere. Earth has some methane, but much less. But importantly, Earth has oxygen in its atmosphere, and Titan has very little. And that is a negative when it comes to thinking about life. But all hope is not lost, as I will describe later. So this is, I'm afraid, a little bit of a complicated looking slide. So for those of you who are new to astronomy and chemistry, don't worry about this. But what I'm trying to say here is that there's what's called a very rich chemistry. So that means there are lots of things, although most of the atmosphere is made of something called nitrogen and methane and hydrogen. On the left, the sun is actually, the light from the sun hits the upper atmosphere, the upper air, the air that's the highest in Titan. And we also get lots of what are called energetic particles from Saturn as well, in what's called its magnetosphere. And these both hit the upper air of Titan. And these are hitting the molecules, they're hitting the atmosphere, and they're causing the gases in the atmosphere to break up and combine together to make other chemicals. And what is happening is that these other chemicals tend to be what are called organic, as I mentioned before, mainly have a sort of backbone of carbon. And those backbone of carbon atoms join together with other atoms such as hydrogen, nitrogen, and form very complex molecules. And the further down you go in the atmosphere, the more complicated they become, until there is effectively a kind of rain of tarry-like substances onto the surface. But it's only by having such a complex chemistry is there any possibility of life on a body. I'm not saying there is life on Titan, but it's not an outrageous suggestion. So this slide is what this is saying. It's all about what's called geological activity. So that's saying that there is motion within the surface underground on Titan. And so that the inside of Titan is being leaked. Any gases that are inside Titan probably do get leaked into the surface. And this is what we get on Earth. And so there is a gas called argon, and a particular type of gas called argon-40. And it only comes, if you detect that in the air, then it can only come from something else called potassium-40. And if you get argon-40, that means, therefore, that it must have come from inside Titan. So this is a really strong fingerprint that scientists use to be able to tell whether any of the air that surrounds a body, a moon or a planet, has come from the inside of that object. And because that has been discovered to be the case, that means that there is gases coming from the inside of Titan into the atmosphere, and that might mean there are volcanoes on Titan. But volcanoes not made of rock, but made of ice. So these are very exotic, but they haven't been proven to exist yet. And there's another finding, also using a different kind of argon called argon-38, and that shows that the nitrogen in the air of Titan probably came from another molecule called ammonia, ice, rather than frozen nitrogen. So that means that the air, most of the air, nitrogen, probably came from rocks that hit Titan, that come from what are called the outer solar system, that bombarded the surface of Titan and gave it its nitrogen, rather than the nitrogen coming from its formation as it grew when it orbited Saturn. So sorry about the wordy. There'll be more pictures a bit later. I just want to talk a little bit about the instruments on the orbiter. So the lander, we've just talked about the lander Huygens that landed on the surface of Titan. But remember, there is also an orbiter which is going around Titan. We're going around, Saturn, orbiting Saturn, and it too has lots of instruments. And these has 6 of them. So it has what's called the imaging science subsystem, and this can take lots of beautiful pictures of Saturn as it goes around Saturn, its rings and its planet, but also importantly, Titan itself. There's another really important instrument, which I'll show you why it's important later, called radar. And what that does is it bounces radar waves that it sends from the orbiter to the surface of Titan, and that allows us to measure how rough the surface of Titan is. The third instrument is what's called VIMS, the Visual and Infrared Mapping Spectrometer. And what that does, it can determine how high the spacecraft is from the surface, and it can look at the surface in infrared as well. It also possibly discovered an ice volcano, but that hasn't been confirmed. There's another instrument which can determine the composition of the atmosphere, and the plasma spectrometer can determine what are called charged particles. So these are particles that are charged. They have a charge on them that comes from charged particles from the sun. That's important for understanding the chemistry of the atmosphere. And there are a couple. The ion and neutral mass spectrometer can also be used to determine the structure of what are called neutral and positive ions in the upper atmosphere of Titan. So that is very complex, but effectively they're all necessary to understand what Titan is like and what it is made of. So this is the first bullet point here is really exciting, because what radar showed is the presence of seas and lakes on Titan, which is a really astonishing find. But they've also been imaged by the VIMS instrument. Glints of light have been imaged, and I've got some beautiful pictures to show you. Another instrument, the ISS, also discovered dunes that are 1 to 2 kilometers wide and 100 meters high that encircle the moon. And they're made of ice coated with hydrocarbons. Clouds have also been discovered that are probably composed of methane. And there's also something called a high gain radio antenna. So that was sending the information back to Earth, but antenna on Earth could look at that signal, and as Cassini went round Saturn and went past Titan many, many times, 126 times, the measurements from that signal allowed the gravitational field of Titan to be measured, and therefore how flexible it is inside, and therefore deduce that it almost certainly has a global ocean of water under the surface. So back to some pictures. This is a beautiful picture of Titan. Titan is not green. This was taken in wavelengths that are longer than the wavelengths of light that we see with our eyes, called infrared. And you can see the beautiful glint of a lake. I think it's Ligaya Mare, actually a sea of near the North Polar Cap of Titan. This is a really beautiful image. So we have seas and lakes, and in the northern hemisphere, they've been found to they are filled almost complete. They are made of almost completely liquid methane. They're surprisingly deep, over 100 meters deep, and many of them are perched on hills or plateaus, hundreds of meters above the sea. So this is, if you were there and to look at that, I think you would find that a really extraordinary sight. The northern seas are filled with methane and ethane, so there are seas and lakes, and there is a lake in the south which has a mixture of ethane and methane. So back to some more images. These are images that show the whole of the north and the polar south regions And you can see in the North Polar regions, you have these very large seas in the upper left-hand side. But on the right-hand side, the lower right, you have many more lakes and not many large bodies. So all the seas, and there are only 3 seas on Titan, are on the upper left. So this isn't properly understood, in fact, why this is the case. And the South Polar region, there is less water at the moment. Less liquid, I should say. Less liquid methane and ethane. And there is a large lake here called Ontario Lacus. It's not the one in blue, it's this footprint-shaped one here. So we only get, most of the liquid is actually at the polar regions, and that's because those are the colder regions. Those are the regions where liquid methane and ethane can exist. So this is another of my favorite pictures of Titan. So this is taken from behind Titan. The sun at this point is behind, is in the distance, 150 million kilometers, 1.5 billion kilometers away behind Titan. And this is a glint of sunlight off a lake called Yingpo Lacus in the Kraken-Mare region. And this was theorized, this was thought to be something that we would find, but it has in fact been found. So that's a very beautiful and unique image. We can't take this image anywhere else in the solar system apart from the Earth. It would be impossible. So these are details, a close-up of the 3 seas of Titan. Pungae Mare, Kraken Mare, and Ligaia Mare. And you can see they're not, that could be an image from the Earth. In fact, it's not an image as we would understand it, as you and I would understand it. It's actually taken by the radar instrument, taken in radio waves. And all of these seas are actually at the same level. So there is a sea level on Titan. This is Ligaia Mare. It's very substantial. It's 147,000 square kilometers in surface area. And it's over 200 meters deep. It's larger than Lake Superior in Canada. And so it is a vast body of methane and ethane, what we call hydrocarbons. And the sum of all the hydrocarbons on Titan is greater than probably 10 times the amount of hydrocarbon that we know exist on Earth. And this, I think, is extraordinary. So what you see in this dashed red line here across the Ligaia Mare is the path of the measurements made by the radar on the orbiter, the Cassini orbiter. And as it passed over the lake, these measurements were made. So you see the results in the bottom right-hand corner. This is called a radargram. And so in this upper panel here, you'll see a thick line, thick horizontal line. And what that is revealing is the surface of the lake. That's the reflection of the radar signals from Cassini off the lake. But then astonishingly, we also get an echo from the bottom of the lake. So if you think about it, we are measuring the profile of a lake to an extraordinary level of precision. A lake that is not a lake of the Earth, a lake of Titan, 1.5 billion kilometers away. That to me is breathtaking. And in the lower part, you can see a close-up of the path that the radar took between the northwest and southeast shore of Ligaia Mare. And now we have another of my favorite pictures. In fact, I suppose most of these images are my favorites in astronomy because they're so amazing. We have a concept, we have something that has been spotted in Titan, and it's been called the Magic Islands of Titan. What could be more wonderful? So it has been noticed that over time, there are features in the lakes, some features in the lakes of Titan that come and go. And this is unique to Titan. We don't see this on the Earth. And if you look at the panels on the left-hand side, you can see that they are taken over a period of many years. There's 6 years, in fact, between the first and the second panel. And in this second panel, you can see a feature which is not present in the first panel. It's this feature in the top left. And that's what's been referred to as Magic Islands. And then subsequently, it's partially disappeared in 2014 and totally disappeared, almost completely disappeared in January 2015. So why are there features coming and going in the lakes? And it's important to remember that this main image is not a photograph. It's a radar signal. So this feature that's coming and going doesn't need to be a solid feature. It could just be something that reflects radio waves very strongly. And it's thought that this may be actually due to bubbles of nitrogen somewhat wonderfully. So the idea is that the upper half of the lake consists of ethane, which is mixed with nitrogen from the atmosphere. Methane and nitrogen, which is mixed together from the atmosphere. And the lower half of the lake is made with heavier ethane. And then the ethane, there is some mixture of the ethane with the methane between the layers due to some process not properly understood. And this releases nitrogen from the lower layers, and they bubble up to the upper layers. And that's what's causing these magic islands. Now, there isn't consensus about this, but I do think that we have possibly spotted bubbles on Titan, really amusing and quite wonderful. The bubbles are thought to be up to 2 centimeters in diameter. So astronomers like to calculate everything they possibly can. So they've even calculated the diameter of the bubbles. Here's Kraken Mare, exquisitely detailed image. And you can see this sort of island here, incredible detail. A massive lake, 400,000 square kilometers in surface area, maximum depth of 160 meters. And amazingly, it's thought that waves may have been discovered on this lake as well. This sea as well, but they're tiny, only 1.5 centimeters in height, which is amazing. So if you were to stand on a shore of this lake and look across it, it would be like a mirror. It would be otherworldly, it would be wonderful. And I think we can agree that on Earth, looking across a lake is a lovely experience. It would be astonishing on the surface of Titan, if you could keep warm enough, obviously. This is Ontario Lacus. This is the footprint-shaped lake that I mentioned before. And what's amazing about this is that even though it's large, 15,000 square kilometers, it's not a trivial lake. It's actually extremely shallow, between 0.5 meter and 8 meters in depth. I think there's a lake in Ethiopia which is similar size and shallowness. So yet another similarity with Earth. Here we have, sorry, I keep repeating myself, yet another similarity with Earth. Here we have the dune fields. The main panel here are the dune fields of Titan. And if you remember, these dunes encircle Titan at the equatorial regions. And you can see they're made of these, they appear to be wonderful parallel lines. And on the bottom right-hand corner, the bottom right, we see them a bit more clearly, and the parallel lines more clearly. And these white regions are not clouds, they are obstructions within the dunes. And the dunes wrap themselves around these obstructions in these wonderful parallel lines. It's not properly understood how they're formed, because the winds at the surface of Titan, as I mentioned before, are very slight. But it's possible they are formed from strong winds that occur only when Titan is going through a change of season between spring and summer, and between summer and autumn during its equinoxes. And in the upper right-hand panel, we have dunes that we see on Earth. Actually, the ones in the Namibian desert on Earth, in the south of Africa, are similar in size, hundreds of meters high, kilometers wide, and hundreds of meters in length to the ones on Titan. So the similarities with Earth are obvious. I should have mentioned, actually, the main panel shows dunes in the wonderfully named Shangri-La region of Titan. And we also have on the surface so-called labyrinths on the solid surface. This isn't liquid, this is the solid. The left panel is taken from a further distance than the similar area, but taken close up. So we have this labyrinthine pattern. And we also get this on the Earth too. And this is a globe. So with all these instruments, with all these measurements from Huygens and Cassini, scientists have now measured and mapped out the geology of Titan in amazing detail. And this shows the entire surface, not just one side, but the entire surface. So that you see the purple are the dunes that I mentioned before, the red craters, the sort of musty red here. These are craters. There are far fewer craters than you might expect if it didn't have an atmosphere, if it was like many of the other moons. But it's the atmosphere that partially stops large craters from being formed because they're formed by large objects hitting Titan, and many objects would actually burn up in the atmosphere. And also there are processes of erosion that cause craters to be filled in and their edges to be eroded away, such as wind, although the winds are very slight, but also liquids that fill them in. There's hummocky regions in orange, and there are plains. Most of the surface are plains. And the blue are the lakes, which, as I mentioned before, are in the polar regions mostly. And this slide shows you the most exquisite images of the whole of Titan, not close-up, but global pictures of Titan. There aren't 6 versions, there's just 6 versions of Titan, there aren't 6 Titans. And I just wanted to show you just how extraordinary the science has become. The exquisite detail. The orange are the dunes, and the other regions, the white, are the icy regions, and other colours are other varying levels of composition. It's a very varied, geologically very varied and interesting landscape and seascape. So there is thought to be, as I mentioned before, a global ocean. This is separate to the lakes and seas on the surface. This is an underground ocean that is thought to surround the interior of Titan. Its size and depth are not accurately known, possibly 100 kilometers below the surface. Between 50 and 300 kilometers depth, I've seen, you'll see various estimates. And this was determined because as Titan orbits Saturn, its distance from Titan varies, and so it gets stretched and squeezed by the gravitational field of Saturn, which is a very massive object. And because it does so, the signal, the orbit of Cassini, as it bypassed Titan, changes, isn't the same, it changes each time it goes past Titan, because Titan's gravity is different. What's called its gravitational field is different every time Cassini flies by Titan. And because many measurements were made, it's established that it probably has this structure. So a silicate core, but similar to our mantle on Earth, but containing a lot of water. There's followed by a layer of high pressure ice. Outside of that, there's global ocean, and on top of the ocean, an outer shell, which is what's called decoupled, so it slides over the water. And then you have the atmosphere, which is organic and rich in organics, as I mentioned before. So we're coming now towards the end. So this Cassini is not the end of our investigation. Cassini-Huygens is not the end of our investigations. There is a future mission to Titan that is almost certainly going to happen. It's called the Dragonfly mission, and it consists of a little a drone, basically, effectively, that you see here in various stages. So this is obviously a mock-up, a graphic which illustrates the drone, which has sort of wings, which will land via parachute. And what it will do is it will land on the surface of Titan, take samples from the surface, whether it's solid or liquid, and then fly off and go to other areas of the moon. And it will do that probably autonomously under its own control, and not controlled from Earth, because it takes about 80 minutes for light to travel from Earth to Titan. So when you see Titan, you see it as it was about an hour and a half ago. And you can't control something in real time with something that far away. So it will have its own algorithms on it that allow it to fly around Titan of its own accord. So what of the far future of Titan? Well, the sun will not remain the familiar sun in the sky forever. Nothing lasts forever. And the sun shines because it has a fuel inside it called hydrogen. And in its core, the temperature and pressure is so high that this leads to thermonuclear reactions in its core. And the result is hydrogen is converted to helium. And in that process, a tremendous amount of energy in the form of heat and light is given off, which is why, of course, the sun is so brilliant in the sky. And it is why I am talking to you now, because without the sun, life would be impossible. So it is the sun that sustains life on Earth. And it's a very stable star, fortunately for us. It's about 5 billion years old, thereabouts. And it's about middle-aged. So in about 5 billion years' time, it will start to run out of fuel in its core. And its interior will undergo a change. And those changes will mean that much higher but much shorter lived reactions will occur in its core. And that will lead to the sun expanding, and it will expand a tremendous to a tremendous size over tens of millions of years. And it will become what is called a red giant. We can see many of these red giants in the sky with the naked eye and telescopes. And it will become so large that it will almost certainly envelop the Earth. So life on Earth will be extinguished, but life on Titan might become possible, because as the sun expands, so the temperature around Titan, in the environment of Titan, will rise. And it's thought to rise to about -80 degrees centigrade. Now, water is still an ice at that temperature, but the water will be mixed with ammonia that we know is in the interior and is almost certainly part of the icy components of the surface, the mountains and the rocks. So that will keep the melting point of water, which will come from the melting of the mountains. It will keep the melting point low, which means that we will get liquid water, probably only for maybe tens of millions of years on Titan. But suddenly we will have all the ingredients of life on Titan. And we know we have organic chemistry at Titan. And so the reactions that we expect on Titan are likely, highly likely, to be similar to the same reactions that gave rise to life on Earth. And so I want to finish really with this slide, which is admittedly a romantic image of what you might see if you were to land on the surface of Titan, but it's not far-fetched. So you see in the upper right the light of the sun, and in the lower right the glints of the light of the sun on a lake which we know exists on the surface of Titan. Remember, those lakes are, some of them, very large, and they are like mirrors. They are so still. We also see familiar features of clouds and hills, and there is the beautiful, this is clearly taken from, this is imagined from a part of Titan that faces Saturn. And as I mentioned before, Saturn would stay permanently in the permanent position in the sky from this vantage point, and you would see its beautiful rings. So amazingly, and against all the odds, nobody would bet on it, but we have discovered that there is an object in the outer solar system that amazingly resembles the Earth in an extraordinary number of ways. So I hope you have enjoyed the presentation. Thank you very much.